Okay, let's talk about some like experimental stuff, sample spaces that you've talked probably a little bit in your previous math classes, probably when you're actually younger. So, an experiment we define as an action or a trial with varying results. So, like for example, rolling a die. Okay, a possible outcome from the result of an experiment, right? From a die, you could get a 1, 2, 3, 4, 5, or 6 if it's a standard die, right? The sample space would be all of the possible outcomes. So 1, 2, 3, 4, 5, and 6. So those should be all review words that you've seen before in probability and odds. Okay, tree diagrams. So let's talk about tree diagrams. So make sure you're filling in your notes here. All right, it's a way for you to visually show how you're finding a sample space. Okay, so when there's multiple things going on. So right here it says when there's multiple actions. Okay, so it says draw a tree diagram, then list the sample space and determine the number of outcomes for each scenario. Okay, so picking a digit 1 to 8, then tossing a coin. Okay, so your first thing in your tree diagram is the fact that you have 1, 2, 3, 4, 5, 6, 7, and 8. Okay, but then it says then tossing a coin. So from each one of your 1 through 8, you would also have the possibility of getting a heads or a tails. Okay, so there's our tree diagram. Okay, the sample space right here, for 1, you could get heads. For 1, you could get tails. For 2 heads, 2 tails, and so forth. All right, so if you look at that, there's 2, 4, 6, 8, 10, 12, 14, 16 possible outcomes. All right. Tree diagram. Next, randomly guessing the answers to the last 3 multiple choice questions of a test, if there are 4 options for each question. Okay, so the last 3 multiple choice questions, 1, 2, 3 questions, right? And question number 1, you would randomly guess A, B, C, or D. 2, same. 3, same. Okay, so the sample space it is saying that for 1, you could get A, B, C, or D. 2, A, B, C, or D. 3, A, B, C, or D. Okay, so that would be 4, 8, 12 possible outcomes. All right, let's look at the next page. Okay, choosing a day of the week, right? So there's 7 days of the week. Then choosing a letter from the word math. Okay, so in number 1, so on the first day of the week, you could do an M, A, T, and H. 2, the same. 3, 4, 5, 6, and 7, the same. Okay, so I listed all of them. So on the first day of the week, you can get an M, you can get an A, you can get a T, you can get an H. Okay, and if you go through all of these, it's really 4 times the 7. So it's 28 total possible outcomes. Okay, so let's look at the fundamental counting principle, which is an easier way than doing a tree diagram. Okay, so if one activity can occur in M number of ways and the other activity can occur in N number of ways, then you basically just multiply the 2 together to get the total number of outcomes. Okay, so choosing a month of the year and a digit 1 through 9, that would be 12 times 9. Choosing a letter of the alphabet, then tossing a coin, that would be 26 times 2. Okay, so I want you to go through and make sure you know the vocabulary, that this is called the fundamental counting principle, and go through these and make sure you're getting correct answers on these. Okay, so I'll slide it down, go ahead and pause your video and get all of your calculations and see if you're correct. Okay, part 2. Probability is just the measure of the chances of something occurring. Okay, so this says the measure of the chance that a specific event will occur. So the probability of an event is favorable over total outcomes. Okay, probabilities have values between 0 and 1. So 0% chance and 100% chance. You can express it as a fraction, a decimal, a percent. I suppose it just depends on the problem and what makes the most sense. Okay, so let's practice some probability right here. We've done these before, but I really do want you to practice. So I'm going to show you all the answers right here. So look at the spinner, look at multiples of 3, prime numbers, check to make sure you're getting the fraction, turn it to a decimal and to a percent, and make sure yours are all matching these, please. Okay, this one. So this set right here. Okay, so what I did was I went through and made fractions for these two. And I actually did do a fraction for this one also. But I want you to check out and see what I did in number 5. Okay, so go ahead and pause your video, work out 2 through 5, and see if you can get the same correct answers. I did not turn them to percents, okay, which is fine. Actually, the directions said to leave them as fractions. And I'm figuring because fractions are an exact answer that may be what you're asked to do. Okay, so if you look at number 6 and number 7, number 6 uses a Venn diagram right here. So I went through and used the Venn diagram to answer all of these. So go ahead and pause your video, see if these answers make sense to you. Don't bother turning them to decimals or percents at this point. Okay, so for number 7, so I'm going to cover that up. So I want you to try to draw a Venn diagram if it helps you. If you can do this without a Venn diagram, it's fine. Okay, but there's a Venn diagram over here underneath my hand that could help you. So go ahead and read number 7. See if you can get A and B correct. Here's a Venn diagram to help you. Okay. All right, let's move on to complements of an event. All right, the complement of an event is the probability of the event not occurring. Okay, since the sum of all of our probabilities in a sample space is 1, the probability of an event not occurring is P, and that's like a little tilde E. Okay, not occurring, right? So you take 1 minus the probability of the actual event. Okay, does that make sense? So you're actually finding the probability of if it actually occurs. And since probabilities are all out of 1, you just subtract from that and you get the leftover. Okay, so go ahead and see if you understand that for 8 and 9. If not, I will definitely go over questions with you. Okay, so 8 and 9 would be the complement of an event. So you take 1 minus whatever the probability actually was. Okay, experimental probability. All right, so it's based on the results of repeatedly trying something. Okay, so go ahead and take a look at this. Look at the spinner. This is what we got. Spun it 50 times. So the theoretical probability would be these right here. Okay, but the experimental probability is what we actually got in our table. Okay, so theoretically, getting an orange is 1 out of 5, correct? But getting an orange, I got 12 out of 50. So it's kind of interesting to see, like, theoretically what would occur and what actually happened. So how do we get these to be close to these? We do trial after trial after trial after trial. We do as many trials as possible. So maybe 50 is not enough. Maybe we would have to do more to get them to be more towards the theoretical probability. Okay. All right.